Hello everyone. A very good evening to one and all of you. I hope I'm audible and visible. So, if not, any one of you can confirm it. So, let's wait for 5 to 10 minutes so that everyone can able to join this session.
Good evening, madam.
Good evening. Sir.
Good evening, madam.
And good evening everyone. So let's start the session. Hello everyone, my name is Pooja Verma, MPMRF Research Scholar from IIT Kharagpur, and the instructor for this course is Professor Jayanta Mukhopadhyay, Department of Computer Science and Engineering, IIT Kharagpur. This is a week 6 live and interactive session on computer vision. So I hope all of you have gone this week video lecture. So So I'm not covering here the theoretical part. So we will solve some numerical questions or some conceptual questions as well, which will be very similar to your assignment question. Okay. So just once, let me confirm whether I am audible and visible, right?
Yes, ma'am.
Okay.
Yes,
Okay.
ma'am.
Okay. Thank you. Okay, so this is the course content for this week. That is a feature detection and description. Different feature detection description techniques you must have been studied through this week video lectures. So let's solve some numerical problems. So question number one is here it is given. Question is gradient along x and y direction at a pixel location xi comma yi can be given as xi plus 1 to xi minus 1 and yi plus 1 to yi minus 1 respectively. The top left corner of the matrix is considered as a 1 1, this one, and the indices increment for x and y axis along horizontal right and vertical downward direction respectively. Okay, that means horizontal in this direction in this and vertically downward and upward this one, like going to this one to this one. Consider 3 cross 3 matrix A, this one. Compute gradient along x, ix and y, iy directions respectively at a center pixel location in A. So our center pixel location is this one, right? Let's say we are saying it I, xi, yi, or you can say that I 2 comma 2 is 0.5 because they are saying that the top left corner of the matrix is considered as a 1 1. So that means I 1 1 is 0.5, this value. Okay, so how we can compute the gradient along x and y directions? Anyone have any idea? Okay, so already we know that this is the center pixel, right? And this is the top left pixel. So let's say that at pixel location, as already we know that this is the center pixel 0.5. So we have to compute the gradient in both the x and y direction. So how we can calculate the gradient? So at pixels say that xi and yi, the gradient in the direction x, ix, let's represent by ix, is calculated by this one, a xi plus 1 is a plus, comma, yi minus a xi minus 1 yi. Okay. Similarly, in y direction, we need to calculate a xi y I plus 1 minus a xi y minus 1. So how we need to compute in both the direction? So let's say x is the right 1 and y is upward or downward. Okay. So already we know that center pixel. So in the horizontal neighbor, this one in this way horizontal. So what will be the neighbor of 0.5 for the center pixel? So I'm just removing it from here, or I can take another slide itself. Okay, so first I have to write the matrix. The given matrix is 0.5, 0.4, and 0.1, 0.2, 0.5, and 0.1 again, 0.4, 0.5, and 0.2. Okay, so already wrote center pixel is I2 comma 2 is 0.5. So first we will calculate the horizontal neighbors, that is in direction y, in x direction, sorry, in x direction, that is same row, because we are calculating for the second row because center pixel is this one. So for this one we calculate this one. That means already told ix plus 1 direction and ix minus 1. Okay, so that is left, or left one I, sorry, that this one is a one first column, second row what will be the value? This is a 0.2, right? Similarly for right, 3 comma 2 is 0.1. That already we have seen in the previous slide. The value ax plus 1 I minus yi, this is it. So it is in the horizontal direction in this one, in the x direction. So we have to calculate for ix first. So a, what is our formula? Xi plus 1 yi minus ax yi minus 1 yi, right? So so this one is ax I plus 1 yi, and this one is ax I minus 1. That means this one yi. Same row, the left and right. So the value, let's say a 3 comma 2 and minus value of 1 comma 2. Okay, so what is it? 0.1 minus 0.2. Here we will get minus 0.1, right? Similarly, we have to calculate for vertical neighbors as well. That is same column. So with respect to center pixel. Okay. So what will be the upward value of? That is a 2 comma 1, right? Yeah, 2 comma 1. So that means first row and second column, that is 0.4, and downward value of with the center pixel is 2 comma, that is 0.5, or you can say that. And in the y direction, what we are, this one is xi yi plus 1 minus a xi yi minus 1, right? So this is a xi yi plus 1, and this one, that upward a xi y I minus 1, right? So here it is, the value is, I'm just writing here first, 2 comma 3 minus a 2 comma 1. That means the, okay, so put the values. So here 0.5 minus 0.4, here you will get 0.1. Okay, so here you have got ix, that means in x horizontally is minus 0.1 and I1 is 0.1. Okay, so in the question they have asked the compute the gradient. So this is the gradient of in along x, I and y, that is ix and iy directions. Okay, so it is directly calculated by this one, this equation. So you can see ix we have got minus 0.1 and iy we have got 0.1. So option A is the correct answer for this question. Okay, so have you understand? So here already in the question given respectively at the center pixel in the location A. So with respect to center pixel, that's why we are moving in this direction, in this direction. Okay, for both horizontal right and left, vertical downward and upward direction in both x and y direction. Here already it is all the things are in the question, it is given. So directly just remember this one in the x direction and y direction, how we take a gradient with respect to the pixel location. So you can calculate from. Okay. So I hope you have understand this question. So now moving to the next question. Okay. So our next question is theoretical one. So the question is choose the correct option. So option A is Harris corner detector finds interest points based on the maximum brightness change moving around a small neighborhood of the pixel. Option B is Harris corner uses gradient information along x-axis only. Or option C is Harris corner point can be used for feature matching as there is a descriptor assigned to each interest point. And option D is Harris corner uses frequency occurrence of pixel information. So what are the different options which are correct? Can you answer for this question at least? This is the based on Harris corner detector. At least make one guess. Then I will define. Okay, so first let's see what is Harris corner. Already you have seen. So this is a theoretical type question or conceptual. So we will see. So the detailed solution is here. So as we know that Harris corner detector is a fundamental computer vision algorithm that used to find interest point in which regions in an image with a high degree of variation within an image region. Okay, so basically Harris corner detectors identify corners by examining a small window or patches of the pixels by using the patches of the pixel or using a small window, and it determines whether this window has a significant change in the pixel intensity when shift in any direction, either it is horizontally, vertically, or diagonally. Okay, so a corner is a point where the brightness or intensity changes significantly in all the directions. So the algorithm can be calculated to changes in the intensity for a small window shifted in a small amount by u or v in both the x and y directions. So the Harris corner is represented by a sum square difference, that is SST, that is also called E comma UV, and second movement matrix if we want to represent in the matrix form. So this is a representation for the Harris corner detector, that is a EU comma V equal to EX comma Y. Here WXY is the window function and IXY is the pixel intensity at the location XY. And already we have said this is a small amount of shift. UV is the small amount of the shift in X or Y direction. So here it is a representation of the sum of the squared difference of Harris corner. And this is the matrix representation of the Harris corner, that is also called second movement matrix. Here WXY is same as a window function and it is IXY. This is a pixel intensity location in X and Y direction. Okay, so already here it is given. The Harris corner detector identifies corners by examining small window or patches of the pixels. Okay, so here it is directly given here. Harris corner detector find interest point based on maximum brightness is moving around a small neighborhood of the pixel. Already we have solved the previous question based on that only. Okay, because a small neighborhood of the pixel we have seen right upward, downward, right left or right. We have calculated with the center pixel. Okay. Now next one is the Harris corner uses gradient information along x-axis only. So already we can see that it is a not only in x direction, it is using the both x and y direction. Okay. So in the next one, so Harris corner gradient information not only uses in x direction, it uses in both the direction as shown in the sum of the square difference and the second moment metric function also the equations in both. Okay, so option B is the incorrect. Now next option is option C. Harris corner points can be used for feature matching as there is a descriptor assigned to each interest point. So this can be a partially correct, but it is a misleading. Okay, while so we can say that while Harris corners are often used as an interest point for a feature matching, the Harris corner detector itself does not generate a descriptor. It only identifies the location of that corner by a separate algorithm, you either shift or SURF, that is scale invariant feature transform or speeded up robust feature. Okay, so this is also not exactly correct. And the last one is Harris corner uses frequency occurrence of the pixel information. So this is also incorrect because the Harris corner is based on the spatial domain analysis, not a frequency domain analysis. So it analyzes the change in the pixel intensity brightness as you move across the images, okay, which is a special property, not a frequency of the pixel value. So correct option is A. Only A is the correct option for this question. Okay. So I hope you have understand. So now moving to the next question. Okay. So next question is if an octave in shift operator has 8 images, then the scale factor by which each image in octave differs from the next image is. So can you guess for this question or anyone of you have any idea how to solve this question? At least try once. Which one will be the correct answer? A. Okay, Sudhakar, right. But how we can solve this question? So as we know that in shift operation, or we can shift is a scale invariant feature transform. Already we know that. And octave span a doubling of the scale, that is a scale of 2, right? If an octave contains n images equally spaced in a log scale, the multiplication step k between the successive images that is represented by k is equal to 2 by n. So the shift in an octave span is scaled by 2, right? And the octave in n images that is equally spaced or multiplicative step k between the successive image that is represented by k is equal to 2 by n. So within an octave, the adjacent that is scale, let's say s, differ by a constant factor k. So if an octave that is if an octave contains s plus 1 images, right? Then, or we can say that here it is s. We can represent k is 2 by 1 by s. So here if an octave in shift operator has 8 images. So total here s plus 1 is 8 images are total. Okay. So to find out s will be 7. Okay. Then you can find k is equal to 1 by 7. Okay. Here total 8 images are there. But if an octave contains s plus 1 images, then k is represented by 2 to the power 1 by s. Okay. The current PC code. Okay, okay, you can join Sudhakar.
Ma'am, excuse me, how
Yes.
S becomes 7? Will you please explain once, ma'am?
Okay. So in basically in shift operator, the octave contains s plus 1 images. Basically in the log scale. S plus 1 images total. So here total images 8 is given. So in the theoretical part. So within an octave, the adjacent scale differs by a constant factor that is k, and it contains s plus 1 total images na, in the theoretical part, s plus 1 images. So here total images given if an octave in shift operator has 8 images, that means s plus 1 is given is equal to 8. So if we want to find s, so s 8 minus 1 will be 7 only na, and to find out the each that how it differs from the different skills. So k is the formula is k is equal to 1 by s, or if n number of images are there, so you can say it n or s. So you
Okay,
can take any representation. So this is the
okay, ma'am. Thank you.
formula. Yeah. So k is equal to 2 to the power 1 by 7. So can you solve it? What will be the value? Can you calculate from your calci? What will be the value you will get? 2 to the power 1 by 7. So if you calculate it, you will get 1.104. Okay. So just to calculate, and can you confirm it in the chat box? What will value you are getting? You just calculate from your simple calculator also. 2 to the power 1 by 7. So you will get 1.104. Okay. That is option A is the correct answer for this question. Okay, so have you calculated? Yeah. So no one is interested to calculate these values. Okay, so I hope you have understand this question. So now moving to the next question. Okay, so next question is given a Hessian matrix H that is 0 0.1, 0 0.01, 0 0.01 and 0 0.1 at an edge pixel in an image. Compute the ratio of its largest and smallest principal curvature. So here we have to calculate the ratio of largest and smallest principal curvature and the Hessian matrix is given. So from this is a symmetric Hessian matrix, right? This is a symmetric matrix because these values are equal, right? So this is a symmetric Hessian matrix is here, it is given. So if it is a symmetric Hessian matrix, so we can directly calculate it. So for symmetric 2 cross 2 Hessian matrix, let's say for a 2 cross 2 symmetric Hessian matrix, let's say it is H A B C. So the the principal curvature we can directly find out by its the eigenvalues are the eigenvalues of the matrix, that is lambda 1 and lambda 2. So that can be directly calculated, which can be calculated by, let's say this lambda 1 to a plus minus b. So you can say that lambda 1 is equal to a plus b and lambda 2 is equal to a minus v. Okay, so can we calculate like this? So can you tell me what are the values of a and v from the given matrix? At least make this session little bit interactive. So can you let me know what are the values of a and v? Then we can calculate. Okay, so from the figure, sorry, from the matrix, you can say that a is 0 0.1 and v is 0 0.01, right? So lambda 1 can be calculated as a plus b, that is 0 0.1 plus 0 0.01. So it will come 0.11, right? Similarly, lambda 2 can be calculated as a minus,
0.09.
yeah, 0 0.1 minus 0.01. So here you will get 0.09. So they have asked the ratio of the largest to smallest principal curvature, right? So principal curvature we have got, that is lambda 1, lambda 2. These are the eigenvalues of the Hessian matrix, right? So the ratio of, so can you calculate and let me know of largest to smallest principal curvature is, that is largest is 0.11, smallest is 0.09, right? Lambda 1 given divided by lambda 2. So after that I'm calculating here. So lambda 1 divided by lambda 2, we will get 0.11 divided by 0.09. So we can write it like 11 by 9, right?
1.22.
Yeah, 1.22. 1.22. So from here you can see that option C is matching 1.22. So option C is the correct answer for this question. Okay. So have you understand? So if Hessian matrix is given, first see Hessian matrix if it is a symmetric Hessian matrix. So directly you can calculate the eigenvalues, or in other way you can also calculate the. So the easy way to calculate symmetric eigenvalues for the symmetric matrix is lambda 1 a plus b and a minus b if it is a 2 cross 2 matrix. Okay. So from here you will get the eigenvalues, and from the eigenvalues they have asked. So that is the principal curvature of the Hessian matrix. So from here directly you can calculate the largest to smallest principal curvature. Okay. So moving to the next question now. So next question is again theoretical. They have asked choose one or more correct options. So option A is an edge will have high maximal curvature but very low minimal curvature. Option B is a key point which is a corner, not an edge, will have high maximal and minimal curvature. Option C is all the edges in an image have both minimal and maximal curvature. Or option D is an edge will have low maximal curvature but very high minimal curvature. So which options should be correct? An edge will have high maximal curvature but very low minimal curvature. Or option B is
Option A.
option A. Okay. And here in the question they have asked that means this is a that can be many options can be correct because they have choose one or more correct options. So what are the other options can be a correct one? Okay, so let's see what are the different options that is correct in detail. So explanation is given here. So an edge in an image represents a boundary where there is a significant changes in the intensity. So in the both directions, along the direction of the edge, the curvature is very low, that is minimal curvature, ideally zero or perfectly straight edge. While perpendicular to the edge, the intensity changes rapidly, resulting high curvature, or that also we can say maximal curvature. So that's why option A is the correct one. Yeah, option A is the correct. And next option is option B. So a corner is a point where two or more edges meet, right? So at a corner, there is a significant intensity changes in the multiple directions, leading to high curvature in all the directions. So that means both the maximal and minimal curvature will be high. So that is making option B is also a correct one. But option C is incorrect because while edges do have both minimal and maximal curvature, the statement implies they are always significantly, which is not true for the minimal curvature along the S direction. And option D is also incorrect as it contradicts the characteristic of the edge of an edges where the maximal curvature is high and minimal curvature is low. So that makes correct answers is A and B are the correct answer. An edge will have high maximal curvature but very low minimal curvature. And a key point which is a corner, not an edge, will have high maximal and minimal curvature. Okay. So option A and B are the correct answer for this question. Okay, I hope you have understand these options. So now moving to the next question. So my next question is again based on the gradient difference. Okay, so question is the top left corner of the matrix is considered as a 1 1, that is this one. And in this is increment for x and y axis along horizontal right and vertical downward. horizontal, that means right, and vertical, downward directions respectively. Right? Consider 3 cross 3 matrix A, that is compute a magnitude and orientation in degrees using the first difference operator at a center pixel. So center pixel is 0.5, that is I 2 comma 2. You can see, because they have asked here the top left, this is I 1 comma 1, that is also 0.5. So already we have solved this question number 1. We have already computed the first order difference equation. So again, we can calculate it again. But here they have asked the magnitude and orientation, or you can say that angle. Okay, before that we have only calculated the gradient difference. Okay, that is first order difference. Okay, so let's calculate. So here we have to calculate with respect difference at the center pixel. So that means center pixel, that is the horizontal right, and that is horizontal left direction, and this is the upward and downward. Okay, so how to calculate the magnitude or difference? So first we have to calculate first order first difference operator. So in the both x and y direction. Okay, for this derivative. So I can say that using the first order center difference approximation for derivatives is Ix is, let's say, I can directly write Ax plus 1y minus Ax minus 1y. Okay, that means x plus 1 in this one, x minus 1 in this one, with at the center pixel. Okay, divided by 2. Okay, because we have to calculate the magnitude. So that's why, yeah, otherwise if we want to calculate only gradient or first order difference, so it is not divided by 2. Okay, and similarly for y also, so it is a x y plus 1 and minus a x y minus 1. Okay, divided by 2. So what are the values of x plus 1 and y? So I'm writing it here. Okay, a x plus 1 and y value is, that means this one in this direction, or we can say if we put the value a 3x plus 1, that means it is at location 2 comma 2, right? So x is 2 and y is 2, so 3 comma 2. So a 3 comma 2, that means third column, and second row is value is 0.1. Similarly, we can say that 1 comma 2, that means this one, first column second row is value 0.2. Similarly, we can calculate upward and downward value also at the center pixel. So here it is a, we can say that second row, second column, third row, so that is 2 comma 3 is again 0.5. Similarly, a 2 comma 1, right? Second column, first row, that is 0.4. So these are the values. So we can put it here, or we can write in this respect also. A 3 comma 2 minus a 1 comma 2 divided by 2. So just put the values. So here it is 0.1 minus 0.2 divided by 2. So here you will get minus 0.1 divided by 2. Here you will get minus 0.05, right? It is a ix. Okay, or you can represent different notations itself, a gx, gy, it also. So here I am representing, but another notation you can use. Okay, similarly for iy also. So iy is a2 comma 3 minus a2 comma 1 divided by 2. So value is 0.5 minus 0.4 divided by 2. So here again you will get 0.05, but it is a positive. Okay. So now we have got the gradient. Now to calculate overall magnitude and orientation, or you can say angle of that magnitude. Take another slide. Okay, so let's first say magnitude of gradient is del I, or that is root of I x square plus I y square. So I x square and I x and I y we have calculated. So here is minus 0.05 whole square plus 0.05 whole square, right? So if you just calculate, you will get 0.005. Okay, whole.
0.707.
Okay, yeah. Okay, you are calculating overall. Yeah, correct one. 0.0707. Okay, so this is the magnitude of the gradient. Similarly, we have to calculate for orientation in degrees, right? Orientation, or you can say angle of the gradient. So it, let's say it is represented by theta. So it is already, we know that the form tan inverse Iy divided by Ix, right? So just put the values. So tan inverse 0.05 divided minus 0.05. So here you will get tan inverse minus 1, right? So typically it is angle of 135, but if we want to, 135 is also can be written as 135 can be written as minus 45 degree, right? We can convert it also, or we can like theta minus 135, right? So theta is overall angle 130 minus 135, okay? Or that is, let's say it is a theta minus 180 minus theta, that one. So it is all 135. If you representation, you can say it is the angle of, it is also written as minus 45 degree. Okay. So that is that sign, or that you will get, so you will get minus 45 itself. Okay. Or you can just normal calculate 135 also represent minus 45 degree. Okay. So the gradient of the magnitude of the gradient is 0.0707, and orientation or angle is minus 45 or 135. So just check with the options. If 135 is there, if 135 is not in option and your gradient is matching, so just 135 is also equal to minus 45. Okay, so here you can check. So no 135. So we have to it in the range of 90 degree or 180. So that's why we have converted back again. So here magnitude 0. So option B is the correct answer. That is magnitude is 0.0707, and the degree or orientation is minus 45 degree. Okay. So have you understand this question? Anyone have any doubt? Okay, so I hope you have understand this question. So now moving to the next question. So next question is again the theoretical one. So question is, which of the following parts are approximated in self compared to shift operator? So option A is computation of scale space. Option B is computation of histograms of gradient direction. Or option C, small Gaussians used in shift are approximated by square integral or box filter. Or option D is extracting feature vector. So which options could be a correct one? Which of the following parts are approximated in surf compared to the shift operator? Anyone have any idea? Please help.
A, C, and D are correct, ma'am.
Okay, A, C, and D. Okay,
Yes.
okay, let's see. Okay, so let's see for first scale invariant feature transform, that is it. So they are following main steps, that is computation of scale space using difference of Gaussians, that is DOG. Next one is key point localization by detecting extrema in scale space. And next step is to calculate the shift is orientation assignment by computing histograms of gradient direction around each key point. And next one, we calculate feature vector extraction by forming a descriptor based on the gradient magnitude and orientation. Okay. And similarly, what we are doing in the sub, that is period of robust feature, that is designed to be a faster than shift. So first one is scale space computation. That is, instead of using the Gaussian filter, surf uses the box filter, right? That is approximation of the Gaussian. And this can be computed extremely fast using the integral images. Okay, so in the one option it is given, right? Surf uses the box computation here or box filters. Now, next one, gradient orientation computation. So Surf does not compute a detailed histogram of the gradient direction as Shift does. So instead of that, it approximate orientation using Haar wavelet responses in horizontal and vertical directions. And next one, feature descriptor instead of Shift 128 dimensional vector from the gradient histogram, Surf uses 64 dimensional descriptor from the sum of Haar wavelet response in subregion. Okay, so the here computation of the scale space. So self approximate exactly Gaussian smoothing using by using the box filters and integral images. That one is a correct A. And the next option is computation of histograms of the gradient direction. So instead of full histogram, self uses Haar wavelet responses as an approximation. So already we have seen in the details what are the main steps. So now small Gaussian used in SIP are approximated using the square integrals or box filter. So already we have seen. So we are using the box filter. This is exactly the self trick to use the box filters or square integrals with the integral images. And here it is also a correct one. Exactly feature vectors. So self approximated this by using the 128 shift to 64 dimensional cell using hard wavelet instead of gradient, but the A, B, and C are the most appropriate and correct answer. So it can be it because it approximate. It may be. So that's why D option is not chosen here as a correct option. That extracting the feature vectors they have written only. If they just re-modified or rewritten by using something hard wavelets or some other parameter things they have written. So that could be a correct answer. That's why D is not a correct one. A, B, and C exactly the correct options. So that's why here chosen the A, B, and C are the correct one. Okay. D can be a correct if they have used like some instead of I mean some changes or some like using her wavelet response they have added like in this question. Extracting feature vectors using her wavelet. They have used it in the options. So that's why it is an incorrect one. Okay. Have you understand? Why D is not D can be a correct option if no other detail is given. Okay. So currently A, B, and C are the correct options. Okay. So I hope you have understand. So now moving to the next question. Okay. So next question is given two features such each of size 4 that is F41424 and G is 9122. Compute L1 and L2 norms between F and G respectively. So here two features of size 4 is given. Now we have to compute L1 and L2 norms between these two features. So how we can calculate it? So here already L1 and L for L1 and L2 norms, the equation or formula is there. So I'm writing here. So L1 norm is calculated by let's say is that is I here number of features, sum of number of features that is Fi minus Gi. Okay, this is calculation for L1 norm and L2 norms is calculated by the square root difference square root sum of square difference of each feature vector that is Fi minus Gi square. So these are the formula to calculate the L1 and L2 norms between the two features vector F and G. Okay, so L1 is the sum of absolute differences, right? As we can see, sum of absolute differences. And while L2 norms is calculated by square root of sum of square differences. Okay, so let's first calculate the L1 norm. Here two feature vectors F and G already it is given. So here it is 4 like number of feature vectors that is 4. I is size 4. So we can say that 4 Fi minus Gi. So we can just like this F1 minus G1 absolute difference plus F2 minus G2 plus F3 minus G3 plus F4 minus G4, right? So the put it is a summation of all the absolute differences. So simple. So just take a difference. So for first one, 4 minus 9 plus 1 minus 1, right? Plus,
Minus 3 answer.
okay, minus. But it is the absolute difference, right? So you will get 3 only. So next one is 2 minus 2, right? Plus last one is 4 minus 2. So here it is minus 5 plus 0 plus 0 here plus absolute of minus 2. So have you studied, I think previously, when it is absolute, where it is written, so when it is taken, so it will consider as 5 only. Okay. So no minus will be there. So it is written as 2, not minus 5 or minus 2. Okay. Have you understand? It is a absolute. So here you will get 7. Okay. Not a minus 3. It is a absolute difference. So if it is a minus sign, so after coming this, you have to always consider plus 5. Okay. Have you understand, Lakavati? How we are getting? Uh, it is
Yes,
a
ma'am.
not
Yes, ma'am.
minus.
I made a mistake.
Okay. Similarly, you have to calculate for L2 norms also. Again, 4. It is a square root of this one. Fi minus gi square. So already we have calculated, or you can again calculate, like 4 minus 9 square plus 1 minus 1 square plus 2 minus 2 square plus 4 minus 2 square. Okay. Now again, here you will get minus 5 square plus 0 square plus 0 square.
5.38, madam.
Okay, yeah, right. So here you will get 25 plus 4. Total you will get 29, and root of 29 value is 5.38. That is correct. So L1 and L2 norms between the F and G are 7 and 5.3. So from the options you can see that option A is the correct for this question. Okay. Okay. So I hope you have understand this question how to solve. So now moving to the next question. Okay. So next question is, note the histogram contains 9 bins corresponding to angle 0, 20, 40, 60, 80, 100, 120, 140, and 160. Okay, the given gradient magnitude and direction in degrees matrices, as it is a for magnitude, it is for direction, in that is in degrees. Okay, respectively, compute a vector representing histogram of gradient corresponding to the given details. So we have to compute a vector that representing histogram of the gradient from this one to represent the corresponding given details. So how we can solve this question? So here different angles are given corresponding the histogram that contains the 9 bins, and their magnitude and direction matrices is also given. Okay, so to calculate this or to compute the vector representation of the histogram, we have to just interpret these data. First, we need to interpret these data. To interpret these data, so that's for both magnitude as well as directions. Okay, so let's say at pixel location at 0 0. So it is, let's say, 0 0 0 1, right? It is a 0 0. Here it is a 0 1. Here it is a 1 0. It is a 1 1. Parallelly for Similarly for this one also 0, 0, 0, 1, 1, 0 and 1, 1, right? So at pixel location 0, 0, what is our magnitude? Can you tell me? Magnitude, let's represent magnitude by M1 at pixel location 0, 0. It is 8, right? And direction we can say that theta 1. It is 80, right? Similarly, we have to take all the for 0, 1 magnitude, let's say M2 is 5 and direction theta 2 is 40, right? And at pixel 1, 0 magnitude M3 is 1 and direction theta 3 is 40 again, and at location pixel 1, 1 magnitude M4 is 8 again, and the direction, that is theta 4, is 0. Angle, corresponding angle is 0. So what we need to do next, assign each sample's magnitude to the nearest pin center, to the nearest pin center. So if here as we can see that the histogram contains 9 wins and corresponding angles are given. Okay. So when these angles will come, because we need to compute the vector corresponding to these angles. Okay. Not a magnitude. So here just remember, here angles are given. Just see and read the questions carefully. Here angles are given. Okay. So let's say when angle theta, I mean 80 will come, let it is a theta 1 is 80. So add magnitude corresponding to that angle, add 5, because corresponding 80 for 80 8, we have to add 8 to that bin. When angle theta, uh, I mean 80 will come. Okay, when angle 80 will come, add 8 to that bin. And similarly, when angle 40 will come, add 5 to that bin. Okay, and next one angle is 40 again. So for again 40, if again 40 will come, or if 40 will come, so add 1 also, add 5, and as well as add 1 to that bit. And when angle 0 will come, the corresponding magnitude is 8. So angle 0, at angle 0 we have to add 8 to that win, to that win. So let's say, so 9 wins corresponding to the angles that is given. So angles that are given, that is 0. Okay, can I remove it from here? Okay, let's take new slide. So the angles that are given in the question, angles given in question is 0, right? Here it is given 0, then 20, then 40, then 60, 80, 100, 120, 140 and 160. These angles that is given in the question. So, and magnitude and angle or direction matrix is also given. So corresponding to that angle or that in that from the matrix we have interpret when this direction will come, that just add that magnitude. Okay, so we can see that when angle 0 will come here, we have to add 8 to that angle. Okay, so at here 0, so we have to add 8 plus 8. Here at there is a no 20, right? So 0, 40, 40, 80 angles are only given and corresponding magnitude for that only it is given. Okay. So when it will 0 come, we have to add 8. When 40 come, then we have to add once 5, then 1. And at angle 80, we have to add 8 again. So here no magnitude is given. So we have to add, 0. Here again, for 40, here it is given. We have to, for 40, we have to add 5 in that way. And next, then we have to add 1 also. So plus 5 and plus 1 we have to add. Now next one is, so again here no magnitudes are given. And for 80, here again it is given. We have to add 8 in that bin. Okay. So plus 8 and again no bin is no given. So plus 0 plus 0 and plus 0 again now right. So here corresponding to that angle, here first one is 8, then again 0, then 5 or 5 plus 1. So here you have to write 6, 6, then 0, then 8, again 0, 0, 0 and 0, right? So this vector you have got 80608 4 times 0, right? So here 80608 4 times 0. So option A only matching. So have you understand this question, how to solve this type of question? So here we have to interpret from the given data. They have asked compute a vector representing the histogram of the gradients corresponding to the given details. So here the gradients magnitude and direction matrices are given, and it is also magnitude and direction in angle it is given, and here angles are given. We have to compute the magnitude to corresponding that angles. Okay, so that represent the vector, complete vector. Okay, so have you understand this question? Anyone have any doubt? Have you understand this question? Okay, so I hope all of you have understand this question. So now moving to the next question. Okay, so next question is weight table to be used in is given as, this is a weight table that would be used where the top right corner is considered as the first neighbor and this order moves clockwise. Okay, top right corner, that means this one, and as a first neighbor, and this order moves clockwise. Okay, in this direction you can say that. Consider a 3 cross 3 neighborhood with grayscale pixel value. It is given. Obtain a single local binary pattern code for this matrix considering the center pixel as a reference. So we have to calculate a single local binary pattern code for the matrix given considering center pixel as a reference. So this is a center pixel. So we have to use center pixel for a reference to calculate the other values or obtain the local binary pattern. Okay, so this is a 3 cross 3 neighborhood with the grayscale pixel. It is given. Now center pixel that let's say 2 comma 2. This is the second row. It is a 172, value of 172, right? So the neighbors in the clockwise order starting from the top right corner from there, because here it is given from the top right corner. So we can just take all the values first. So A00 is 90, A01 is 200, A02 value is 140. Okay, A10 value is 180, again A11, or yeah, it is a 11. 172, that is a center pixel, and the A12 is 100. Okay, now again 20 is 170, A21 is 181, and A22 is 152. Okay, now what we need to do, compare each pixel, is this pixel with the center pixel. Okay, we need to compare and assign 1 if never value is greater than or equal to center pixel, and 0 otherwise. So we have to compare, let's say, compare each neighbors with center pixel, assign 1 if its neighbor value is greater than and 0 otherwise. Okay, so center pixel is 172. So first let's compare and take. So center, we have to, you can compare, I mean, either take a difference or you can directly compare. So first you can compare 172 to 90. So 172 is greater, right? Minus 90, you can say, or you can say 172, that means center pixel is greater than 90, that means this pixel. I am just starting from there, this side. Okay, so just assign 1 in that case, right? Is greater than. Now again 172 again greater than, sorry, it is less than 200. 200 to the next pixel. If you take this one, A01, so assign 0. Now again 172, it is 140, so that means this one is greater than, so again assign 1. So we have, similarly we have to calculate for all the values in the given matrix A. So I'm just taking the another slide so that we can write it. So I can write here center pixel, and here we can write the neighbor. You can make a call one table also, so it is easy to neighbor pixel. So center pixel is 172, and neighbor pixel you can write it and just put 90, 200, 140, then again 180, 172, 100, 170, 181, and 152. So here it is a same center pixel. So it is not required because we are comparing with respect to center pixel itself. So we can remove it also from here. Okay. So here I can write 100, then 170, here 181 and 152, just 100, then 170, 181 and 152. So just compare it with this center pixel. So here it is greater than, so assign 1. Here 172 is less than 200, so assign 0. Here again 172 is greater than 140, so assign 1. Here again it is less than, so assign 0. Again 172 is greater than 100, so assign 1. Again 172 is greater than, again assign 1. Here 172 is less than, assign 0. 172 again greater than, here it is a less than, so assign 1, right? Is it correct?
Yes, ma'am.
Or what we need to do, one thing. No, actually I have little bit here. Assign 1 if never value is greater than or equal to. That means if it is greater than, then we have to assign 1. So just a minute. This is it. I have written here correctly, but interpreted well. Compare each natural values. If it is, if never value is greater than, then assign 1. If otherwise 0 if neighbor value is greater than. So that means here neighbor value, it is a neighbor value. So if it is greater than, then we have to assign 1. So here again 0, here it is greater than, so we have to assign 1. Again it is less than, so 0, it is greater than, here 1, here it is 0, and here 0 again, neighbor value is greater than, but here here it is greater. So we have to assign 1. Here it is less than, so again assign 0. Now it's correct. So have you understand? If never value is never, means neighboring pixel is greater than, then we have to assign 1, otherwise 0. Okay. So here we have got the binary sequence. Binary sequence we have got, right? And the with the respect to the, here the weight table is given to calculate from here. So the weight table is given, that is 2 to the power 6, 2 to the power 7, 2 to the power 0, here 2 to the power 5, here it is the center pixel, so no allocation, 2 to the power 1, 2 to the power 2, 2 to the power 3, and 2 to the power 4. Here it is given in the question, this one, this table. Now we have to calculate the corresponding weights with this binary sequence. Okay, for the binary sequence correspond to the weight. So we have to calculate the corresponding weight with for this binary sequence. Here calculate corresponding weight for binary sequences. So let's say, so similarly for, so corresponding the pixel 9, the binary sequence allocation is 0, for this one 0, right? And the corresponding weight with respect to that, this one is, right? I can write the another table met A also so that we can not forget 140 here, 180, 172, 100, 170, 181 and 152. This is a binary sequence for this one. So binary what we have allocated for 90 it is 0, right? So 0 corresponding weight is 2 to the power 6. So whatever you will multiply you will get 0 only, right? Again then for 200, so for 200 the corresponding binary sequence is 1. So for this 2 to the power 7. So what will be the value calculate to the power 7? Then again for 140, just let me know what will be the value for 2 to the power 7. And for what will be the binary sequence for 140? It is a 0. So 0 to the power 0. Here 0 you will get. Again calculate for 180. The binary sequence is 1 into 2 to the power 5. So can you calculate? 170 it is a center pixel. They don't need to calculate. So for corresponding 100 it is 0 to the power 1. And for 170 it is a 0 again. It is a 2 to the power 4. For 181 it is 1 into 2 to the power 3 corresponding weight, and 0 again for 152 and corresponding weight is 2 to the power 2. So here you will get 0, again 0 and here 0. So can you calculate 2 to the power 7? 2 to the power 7 you will get 128. Again 2 to the power 5 you will get 32. Here 2 to the power 8 you will get 8. Okay. So corresponding weight for the binary sequence we have to calculate it. So now how we calculate the LBP, local binary pattern code. So this is the local binary pattern. It's some of the weighted binary values. So binary values we have calculated from here, and their weight table is also given. So it is called the some binary weighted value. Okay. So these values are called binary weighted binary values. So LVP code is sum of weighted binary values. So just we have to take a sum of all the weighted binary values. So 0 plus 128 plus 0 plus 32 plus 0 plus 0 plus 8 plus 0. So what value you will get? 40. 32 plus 840 plus 128 you will get 168. So LVP code that you have got, that is 168. Okay, so just check with the answers. Yeah, 168, that is option B. So option B is the correct answer for this question. So have you understand this question? Have you understand this question? Anyone have any
Yes, ma'am.
doubt?
Yes, ma'am.
Okay, okay. So moving to the next question. So next question is, consider a set of parametric equation x that is equal to t cube plus 2t square and y is equal to t square plus t, representing a 2D curve, that is represent a 2D curve. Compute a tangent vector at t is equal to 2. So can you let me know how we can calculate this? So here given x is equal to t cube plus 2t square and y is equal to t square plus t. Okay, so here that it is represented 2D curve. Compute the tangent vector at t is equal to 2. So to calculate the tangent vector at t is equal to 2, first we have to take the derivation with respect to t to represent the 2D curve. Okay, compute derivative to represent 2D curve. So first, let's say x dash, that is dx divided by dt, that is equal to, if you just take a differentiation with respect to t, you will get 3t square plus 4t, right? Similarly, for y also, that is represented by y dash. So dy divided by dt, here you will get 2t plus 1. Okay, now they have told that tangent vector at t is equal to 2. So tangent vector at t is equal to 2. This is the tangent vector, that is x dash, let's say, at t equal to 2. So 3 into 2 square plus 4 into 2. So 12 plus 8, right? We will get 20 here. For y dash, let's say 2 into 2 plus 1. So here you will get 2. So 2D vector at 2D curve at t is equal to 2, that is represented by x dash, y dash is 20, comma 5. Okay, so that makes C is the correct answer for this question. Okay, okay. So I hope you have understand this question.
Yes, ma'am.
So now moving to the next question. Now next question is, consider the following matrix representing four sample data points, that is 1 2 2 1 3 2 2 3 as a X matrix is given. Compute the covariance matrix using data point from X. We have to compute the covariance matrix using this data point. So here four samples data points are given. Now to compute the covariance, first we have to compute the mean, and then we have to compute the deviation matrix using the data point and the matrix X. So first we have to compute the mean vector, let's say, to compute the covariance matrix. So the mean vector mu is calculated by taking average of the corresponding data point. So mean is, let's say, mu. It is two data for in the x and y it is given. So we have to compute the mu x and mu y, right? So just take average of the x, all the x values and y values. So here we can represent it 1 plus 2 plus 3 plus 2, like 1 plus 2 plus 3 plus 2. For x, how many data points are there? It is 4, right? So 4. Similarly, we have to calculate for y also. So 2 plus 1 plus 2 plus 3 plus 2 plus 3 divided by 4. Now mu x, mu y, that we will get, that is equal to
Both are
8,
2, 2.
yeah, 8 by 4, 8 by 4. So you will get 2 and 2. So this is a mean vector that you have got from the data points. Now we have to calculate the deviation matrix. Now calculate deviation matrix. So how we can calculate? Let's say it is x dash. It is represented by x dash. So minus of this value to mu. Okay. that is x minus mu x1 mu x, you can say it is in x direction, it is a y again. Take like this one, and here x2 minus mu y, x, let's say 3 minus mu x, and x4 minus mu y. Similarly, we have to calculate, just take a minus to calculate the deviation matrix. So first value is 1, so 1 minus 2. Similarly for here it is 2, so 2 minus 2, because mean vector is 2. Here again 2 minus 2, 1 minus 2, 3 minus 2, 2 minus 2, and 2 minus 2, 3 minus 2. Okay, so deviation matrix x dash, finally you will get minus 1, 0, 0, minus 1, here 1, 0, 0, 1, right? X dash, this is a deviation matrix. Okay, that you have got. Now how we compute the covariance matrix? So the covariance matrix is calculated by matrix is calculated by, that is, let's say it is represented by C, that is x dash transpose x dash divided by n. So here this x dash is deviation matrix, already we know that. So it is a x dash transpose x dash, here number of samples is 4, so 4. Okay, so first we need to calculate x dash transpose and x dash, right? So x dash already we have calculated in the previous slide. So now first we need to take the transpose. So change row into column, column into row of this vector x dash. Okay. So in the first row you will get minus 1, 0, 1, 0. In the second row you will get 0, minus 1, 0, 1. Okay. For x transpose. So minus 1, 0, 1, 0, 0, minus 1, 0, 1. And we have to multiply with x x dash. So again minus 1, 0, 0, minus 1, 1, 0, 0, 1. So can you calculate these two matrices? We have to just row into column, then again row into second column, row, second row, first column, second row, second column, right? So here you will get 1 plus 0 plus 1 plus 0. Here you will get all the zeros, right? Because 1 into 0, 0 into 1, minus 1, 1 into 0, 0 into 1. Again, similarly for this one, 0 into minus 1, 1 minus 1 into 0, like this, you will get all the zeros here also. In the next one, you will get 0 plus 1 minus 1 into minus 1 plus 0 plus 1. So here you will get got 2, 0, 0, 2. So this matrix X transpose X dash, you have got this one. Now the covariance matrix C is 1 by 4 into 2, 0, 0, 2. So if you just calculate it, you will get here 1 by 2, 0, 0, 1 by 2, right? Or we can write it 0 0.5, 0, 0, 0 0.5. So this is our covariance matrix C, 0 0.5, 0, 0, 0 0.5. Okay. So from the options you can see option B is the correct answer for this question. Okay. Okay. So I hope you have understand this question. So now moving to the next question. Again, this type of question we have solved. So you can say that this is a, you can just do practice with this question. So the question is, the top left corner of a matrix is considered as 1 1. That is this one, top left. And indices increment for x and y axis along horizontal right, that means in this direction, and vertical downward, that means in this direction, respectively. Consider 3 cross 3 matrix A. This is given. Compute the magnitude and orientation. Orientation in degrees using the first order first difference operator at a center pixel, at the center pixel. That is, this one is our center pixel, 0.2 respectively. Now we have to calculate the magnitude as well as orientation, or you can say angle. So already we have calculated this type of question. So would you like to practice this question, or I will solve it quickly?
We can skip, ma'am.
Okay, so I mean, let me just solve it because other person,
Only
because
answer.
uh, because other person actually will not, because it some most of the people have not joined this session, most of the session. So I think they are
Please solve it, ma'am. Please solve it, ma'am.
I think they are watching it later in the YouTube. So that's why we have to solve. So I'll just
Yeah, yeah.
solve it
Please solve
quickly.
it, ma'am.
Okay, so this matrix is given. So center pixel is, let's say, center pixel, it is a 2 2, that is 0.2, right? 0.2 it is given. Now what are the values? Can you let me know? AXI plus 1 plus YI and AXI minus 1 YI, AXI YI plus 1 and AXI YI minus 1. So with we have to see in the center pixel, and then we have to calculate AXI plus 1 YI. So XI plus 1, that means it's this one, XI minus 1 is this one, YI plus 1 is in this direction, YI minus 1 in this direction with the center pixel. So XI plus 1 YI is 0.3. Here it is a 0.5. Here it is a 0. Again 3, and here this value is 0.1. Okay. Now, the first order difference we need to calculate using, because they have asked using the first order difference, we have to calculate the magnitude and orientation. Okay, so let's say we have to calculate the first order difference magnitude. So first order difference, first take, let's, I'm representing here again gx. So a xi plus 1 yi minus a x minus a xi minus 1 iy, and it is equal to divided by 2, right? So here, what is this? 0.3 minus 0.2 divided by 2. So here minus 0.2 divided by 2. So here you will get minus 0.1. Okay. Similarly, you have to calculate for gy. Here for gy, it is a xi y I plus 1 minus a xi yi minus 1 divided by 2. So again, the value is 0.3 minus 0.1 divided by 2. So 0.2 divided by 2. Here you will get again 0.1. Okay. So here gx and gy values you have got. Let me just so gx and gy you have got. Now we have to calculate magnitude and angles. So let me take another slide. So just a minute, I have been disconnected.
Madam Joy.
Yeah, actually I got
Thank you.
disconnected. Let me.
Ma'am, voice not audible.
It's audible now? Yeah. Hello.
Yes, ma'am. Yes, ma'am. Now.
Okay. Are you able to see my screen now? Okay. So here we have calculated gx and gy. Now we have to calculate the magnitude and orientation.
Ma'am, screen not visible.
Now it's visible or not? Already I have shared. Now it's visible.
I think for me it is a problem.
Okay, so I don't know whether any problem is going on. So now it's visible.
Yes, ma'am. Now visible, ma'am.
Okay, so Till now we have calculated the gx
Yes,
and
ma'am. Yes,
gy.
ma'am.
Okay, now we have to calculate the magnitude. So already we know that for calculate the magnitude, that is m, it is root of gx square plus gy square. So gx and gy square we have calculated, that is minus 0.1 square plus 0.1 square. So can you just calculate and let me know what will be the value? So here you will get 0.2, and this value you will get, I think, 0.1414. Okay. Similarly, we have to calculate the orientation. Orientation in degrees, that is theta. So the formula is tan inverse gy divided by 3x. So it is a tan inverse 0.1 divided by minus 0.1. So again here you will get tan inverse minus 1, and which is equal to 135, and the 135 is equal to or minus 45. Okay, so the magnitude that you have got 0.141 and minus 45. Okay, so just tick in the options, you will get option B is the correct answer for this question. Okay, okay, so I hope you have understand this question. So now moving to the next question. This is again the same type of questions we have solved previously. So if an octave in shift operator has 10 images, that means here the total shift operator has total 10 images. That means s plus 1 is equal to 10. So for s you will get 9 here again. Then the scale factor by which each image in octave differs from the next image. So the scale factor, already we know that, factor by which each image in octave differs from the next image is represented by k, and k is equal to 2 by 1 by s, and here s we have got what, 1 by 9. So can you calculate and let me know what will be the value? 2 to the power 1 by 9. So you will get here 1.080 if you calculate it. Okay, so that makes option A is the correct answer for this question. Okay, okay. I hope you have understand this question. Now moving to the next question. Actually, we are running out of time, so I have to calculate few more questions. So I'm ready. Already we have solved this type of question. Okay. Now next question is, again it is based on the L1 and L2 norms. Hello everyone. Sorry for the inconvenience. I hope I'm visible and audible. So last time we got disconnected, and but we had calculated the value of the magnitude, right? Sorry, L1 norms we have calculated. Now we have to calculate the L2 norms. Okay, L1 norms we have calculated here, that we have got 10 for this. And now we have to calculate L2 norm, that is, already we know that it is a square root of summation of all the squared value. So f minus g whole square. So already we have calculated f minus g values, right, in the previous one, L1 norms. So here 2 minus I we have got 3. minus 3 square plus here it is 1 square plus minus of 4 square plus 1 square again, here 0 square and 0 square plus minus 1 square, right? So if you just add and take a summation of all those, so here you will get 9 plus 1 plus 16 plus 1 plus 1. Okay, and overall value you will get 28 root of 28, and for that you will get 5.29. Here L1 norms we have calculated that we have got 10, and L1 norm we have got 10, and L2 norm we have calculated 5.29. So that makes option C is the correct answer for this question. Okay, so I hope you have understand. Now moving to the next question. Now next question is again we have to calculate the L1 norm, and here feature size, the two feature size of 5 is given. So already we have calculated many times. So L1 norm is absolute summation of the absolute summation of the summation of the two vectors. So here again we have to make, so 3 minus 7 plus 2 minus 2 plus 4 minus 5 plus 5 minus 3 plus 1 minus 2. Okay, so here you will get minus of 4, here plus 0 plus minus 1 plus 2 plus minus of 1. If you again just take it, so 4 plus 0 plus 1 plus 2 plus 1 you will get. If you add all those values you will get 8. The L1 norms of between F and G you have got 8. So the answer is 8. Okay. Okay. So I hope you have understand. So now moving to the next question. Now next question is based on the theoreticals and conceptuals. The question is, what is the primary advantage of LBP over simple pixel-based feature or for texture analysis? The options are: it is a computationally more expensive, it is invariant to grayscale changes due to its thresholding nature, it captures color information better, it requires larger neighborhood or a feature computation. So what are the options that are correct? Okay, so let's see in detailed solution. Option B is the correct answer. It is invariant to grayscale changes due to its thresholding nature. So solution is, the core of the LVP algorithm involves thresholding a pixel's neighbors against the center pixel. Already we have seen and solved in many questions. And the resulting binary code is based only on the relative intensity, not on the absolute value. So this makes LVP inherently robust to monotonic changes in the grayscale, such as those values caused or changes in the illumination. This is a significant advantage over other methods rely on the absolute pixel values. So option B is the correct answer. It is invariant to grayscale changes due to its thresholding nature. Okay. Okay, so now moving to the next question. Next question is again the theoretical one. Which of the following statements about uniform LBB pattern is true? Option A is a uniform LBB pattern has at most two bitwise transition, either 0 1 or 1 0. Right? That is correct. A uniform LBP pattern is created by a 1 pixel radius and 8 neighbors. Option C is a uniform LPP pattern is a special case that always results in a decimal value less than 100. Or option D, a uniform LPP pattern is not rotationally invariant. So let's see in detailed solution. So option A is the correct answer. Already we have solved one question in the weighted binary sum one. So a uniform LPP pattern has at most two bitwise transition, that is either 0 to 1 or 1 to 0. So a uniform LPP pattern is a special type of LPP code that contains at most two bitwise transition from 0 to 1 or 1 to 0. That example is either it is a 0 0 all 0, so 0 transitions, and here 0 1 1 1 1 1 0. Here two transitions are there either, and here again no transition. So these patterns are considered most stable and dominant in many textures. Okay, so LVP, the uniform LVP pattern has at most two bitwise transition, either 0 to 1 and 1 to 0. That is option A is the correct answer for this question. Okay. Now next question is, if the covariance matrix of a data set is a diagonal matrix, what does that tell you about the variable in the data set? So options are, the variables are all identical. The variables are all linearly independent. The variables have zero covariance, meaning they are uncorrelated. The variables have a perfect linear relationship. So which options can be a correct one? Okay, let's see the detailed solution. So option C is the correct one. A diagonal covariance matrix means that all the off-diagonal elements are zero. These off-diagonal elements represent the covariance between the different variables. A zero covariance value indicates that there is no linear relationship between those variables, meaning they are uncorrelated. So that makes the variable has zero covariance, meaning they are uncorrelated. So that makes option C is the correct answer. The variables have zero covariance, meaning they are uncorrelated. Okay, option C is the correct answer for this question. Now, quickly moving to the next question. What is the main reason for introducing uniform pattern in the LVP algorithm? Options: to make the LVP code rotationally invariant, to reduce the dimensionality of the feature vector, or option C, to detect more complex texture patterns, or option D, to ensure that the LVP code is always an odd number. So what is the main reason behind introducing the uniform pattern in the LVP algorithm? Let's see in the detailed solution. To reduce the dimensionality of the feature vector. Okay, option B is the correct answer. The main reason to introduce uniform pattern in LVP algorithm to reduce the dimensionality of the feature vector. Let's deep down in the detailed solution. So in a standard 8 neighbor LVP, there are 2 to the power 8, that means 256 total possible combinations or patterns. So many of these patterns are rare in the real world images and sensitive to the noise. So the concept uniform pattern was introduced to address this problem. The uniform pattern is defined as one of the most two bitwise transition, either 0 to 1, 1 to 0, to its circular bit string. So, so that's why we have introduced the uniform LVP pattern to reduce the dimensionality of the LVP histogram. Okay. Now moving to the next and last question, that is, a self-descriptor is constructed by dividing the neighborhood around the key point into 4 cross 4 grid. Each subregion cell has 4 values in its gradient orientation histogram. What is the total dimension of the final self-descriptor vector? So here it is given, a self-descriptor is constructed from the 4 cross 4 grid. A subregion, each of these subregion cells contains 4-dimensional gradient orientation. So the number of subregions is 4 cross 4, that is total 16, and dimension for each histogram is 4. The dimension of each histogram is 4. So the total dimension of the descriptor vector is equal to, that is, number of cells, cell dimension. So total number of cells is, we have calculated the 60, and the dimension of each histogram is 4. So that is 64. So that is the option. What is the total dimension of final self descriptor vector is? So total dimension of final self descriptor is 64. Okay, that makes option D is the correct one. Okay, so now the questions have been completed. So thank you everyone. Thank you for joining this session. And I'm sorry because in between the session got disconnected. So I am facing some issues. So that's why session got disconnected. By the way, I will upload all these videos and remaining solutions as well. So okay, thank you everyone. Thank you for joining this session.